All right. Okay. So we talked about the fundamental principle of counting, and in essence, the word itself, right? Fundamental, everything starts from this principle. So if you understand this principle well, and we talked about this last time, right? It's kind of like a multiplication, right, of different outcomes for each event that occurs. And we can think of it as a tree diagram of different events that are possible. And instead of going through every single branch, we're just clumping them up into little like groups of branches. And that's where the multiplication is embedded in this principle of counting. And that's why it makes sense to multiply these numbers when we have these numbers for the number of events per a number of outcomes per event. So uh, these words are very specific, right? We have outcomes, which are like what can occur, and events, which are also known as experiments of an action occurring. So we have an action, an event, or an experiment, and for each of those situations, there are certain outcomes that can arise. So once we're able to enumerate every outcome, for every event, we can clump them together by multiplying those number of outcomes to figure out the total number of possibilities that can occur. Once we get really good at that, then probability becomes much more um, intuitive and understandable. If we don't know how to count, then probability becomes a mystery, really. Okay, so let's continue with uh, learning how to count. So just to, get our feet wet again, let's see. We talked about the last example here was the only example we talked about was the license plates, right? How many license plates we're able to create. Given the fact that the first three places of the license plates are letters and the last four places are digits. And we're able to figure out that there's 175,760,000 license plates that are possible. Okay, so let's see if we can now move on to what are called permutations. So permutations. So you may have heard of this for some of you who have talked about counting before. Permutations is the term for an arrangement. Okay, so it's an arrangement of objects where the order matters. So we'll discuss a bit more what it means for some in order to matter. And then this will appear again where we're going to be considering arrangements of objects where the order does not matter. And those are called combinations. Okay, so let's talk about when order does matter. And so when you talk about order, there's different situations in our daily lives where order of things do matter, right? So what's one of those places where order does matter? It's in a line. So when you form a line for anything, for you want to buy tickets to the next show, you want to buy the tickets for the next movie, you want to line out, you want to create a line outside to get the newest sneakers that came out, right? We care about who's first, who's second, and who's third. And so then the question naturally arises is, let's suppose, right? Let's suppose there are, let's make it like 8 people, right? 8 people waiting in line to buy tickets, right? To buy concert tickets. Not too impressive of a concert, I guess, because only 8 people, but this is just for our example here. And then someone says, you know what, how many ways are there? How many ways are there to arrange or yeah, to arrange the people in that line. The 8 people in the line or on the line. I know there's the grammatical here, on the line. So again, this is a simple example. So we have 8 people waiting in the line. And then someone says, how many possible versions are there of this line with 8 people? And can anybody think of how to do this, given the fact that we talked about the principle of counting, and then Chaitanya says, a lot of people are saying now, 8 factorial, which we're going to talk about what that is, but there's an 8 with the exclamation point. So how do we get there, right? Let's say we didn't know what factorials were. We haven't had that yet, right? Well, we could think about this little slot thing or these blank spaces that I discussed last time, right? So for each space, you got 1, 2, 3, 4, 5, 6, 7, 8. So you have 8 spaces on the line, right? So these are 8 spaces on the line. And so, of course, we're going to say this is the first, right? Whoever's first, this is second, so on and so forth. And this is the last. This is the guy in the person in the final position of the line. And then we have 8 people to choose from. So for each space, we have 8, because we have 8 people on the line, we have 8 spaces, right? So we say we have 8 choices for the first position. We have 8 choices we have 8 people to choose from. That's why we have 8 choices. And then we say, once we make that decision, right? This is kind of just to give you a visualization. This is kind of like what we discussed, right? With this, we had 1, 2, 3, 4, 5, 6, 7, 8. So this is like for the first position, right? I can have choice A, B, C, D, E, F, G, H. Of course, I'm just using letters. Let's say these letters represent the initials of the first name of each person. Each person has a name from A through H, right? And this is the first position here. And then once we make that decision, then we have how many choices left after we make, for example, let's say the first person is named Alex. And so we have Alex there, right? In the first position. And then how many choices do we have next? We got 1, 2, 3, 4, 5, 6, 7 left because we already chose Alex. We have 7 people left. So we have B, C, D, E, F, G, H, right? And do you guys see what's gonna be the next what's the next, like how this is going, right? This is going down descending order, right, Fernando? Yeah, everyone's understanding, hopefully, what's occurring afterwards. And then the thing is, we're going to do this for every single choice for the first position. So we have 7 choices for B. Then we have 7 choices after we choose C, so on and so forth. So instead of drawing this whole diagram, which is going to be really long and enormous, right? We can just numerically compute it. And so that's not going to take too much of our time because we have computing power that helps us. So I want to say is I hope you guys understand why these numbers are going in descending order, and why we're multiplying them. Because at the last position, we've chosen 7 spaces for 7 people already. So there's only 1 choice left after every position is filled up to the last point. And this is a very special product. This is a product of numbers that are descending from 8 to 1. And we call this 8 exclamation point. We'll write it as 8 exclamation point, but this is really what's called 8 factorial. So we got 8 factorial. So the word factorial is going to be part of our lexicon as we discuss counting. So factorial just means take that number, that whatever is in front of the question, not the question mark, exclamation point, whatever that number is, just multiply every number that comes after or in descending order until you get to 1. And when you do 8 factorial, if you put it in your calculator or if you try to compute it yourself, which I would recommend to eventually use a calculator because these factorials can get pretty big. A factorial is 40,320. Thank you, Christian. Yep. So there's 40,320 ways to arrange 8 people in a line. Now, that's a lot of ways, isn't that? Like 40,000 ways just for 8 people. I can rearrange 8 people in 40,320 different ways. I could create a line. I could create 40,320 different versions of a line with just 8 people. And I just want you to see that this problem, like I can change up the context of this problem in so many ways. It doesn't have to be 8 people in a line. It could be 8 cars in a driveway. If you have that long of a driveway, and if you have that many cars, you can create 8, I don't know, 8 markers of different colors. And how do you arrange it on a blackboard? Or there's so many different examples of arranging 8 objects. So you see how you can abstract this now? You can generalize this to just to a more general idea of arrangement of objects. And you can decide what the object is, and you can decide what kind of ordering you're creating. But the idea is that 8 factorial represents how many ways you can arrange 8 things in an order. And so I think one of your questions in your homework is, how do you arrange, for example, you have a bookshelf and you have, it's I think 12, some people have different numbers. You have 12 books on a bookshelf. How many ways can you arrange 12 books when you want to put every book on the bookshelf? And then exactly, Sharoz, it becomes 12 factorial. It kind of now becomes natural to say, oh, it's this factorial, it's that factorial. And that's, again, very good. I'm glad you did that yesterday. And that's how we start now to build up the techniques of counting. So we go from principle of counting, and then we start talking about factorial, which leads to permutations. And then combinations is what really gets things interesting, the combinations portion of it. Okay, so any questions about this? Any questions? Does that make sense? Anybody has any comments? No questions. Okay, so I hope this is simple enough. All right, and of course we can now get a little more sophisticated with this. Not sophisticated so much, but more, more interesting examples. So let's say, so when does order matter? For example, in a race. So let's say we have, is there 8 runners? Yeah, there usually are, right? So for there are 8 track and field sprinters in a 100-meter race. And of course, right, we just had the Olympics. Not everybody wins. That's the whole point of competition, is that there must be a winner. There must be a first place, somebody who goes first place, somebody who goes second place, and someone who goes third place. And those are the, given history and tradition, we consider those 3 places as worthy of being given a prize: gold, silver, and bronze, right? So then the question is, how many different ways are there to give prizes to the 3 people who win? So how many ways, or in other words, you can say, how many ways are there for 3 sprinters of the 8, of course, to finish in first, second, or third place? So does anybody have an idea of how we can approach this? And so I see some people in the chat saying 8 times 7 times 6, question mark. That's right. And why is that right? Well, we only care about the first three space, like only the first three finishers, right? We only care about those. So we don't care about the rest, unfortunately. So we care about the first place, we care about the second place, and we care about the third place. So then we say, hey, what's the possibilities of somebody finishing first? Well, there's 8 sprinters. So I have 8 possibilities, right? I'm just talking about all possible ways for someone to finish in first place. Out of the 8 people, there's 8 different people to choose from. Once that first person makes, once that sprinter makes it to first place, then we only care about the next place, which would be second place. But once you have one person that finishes, you have 7 people left. So we have 8 times 7. And then once we chose those, once those first and second place, um, once those first and second place sprinters are finished with the race, then we only care about the third place, which there's 6 left to choose from. And I'm gonna say what this is. You can actually compute it yourself, right? 8 times 7 times 6. And when you do that, there's 336 ways, right? For a there's like 336 possible ways for 8 people to finish in the first 3 places. Yeah, so Alexandra came up with a question and she said, could you write this as 8 factorial minus 5 factorial? Now, this is when, that's a great question. And the simple answer is no, you cannot, but try to understand why. If you do 8 factorial, you're considering, I know what you mean, because I think what you're thinking about is 8 minus 5 is 3, right? But in factorial land, 8 factorial, you're dealing with 8 spaces. Like you're basically considering 8 factorial ways, right? 8 factorial ways is exactly what we just found, 40,320. And then 5 factorial would be how many ways do you finish the first 5 in the first 5 places? So when you subtract 8 factorial with 5 factorial, you get a number, right? Because 8 factorial, you can compute it. 5 factorial, you can compute it. But when you subtract them, there is no connection with the number 8 factorial and 5 factorial. When you subtract them, there's no connection for you to do so. And some people here have suggested 8 factorial over 5 factorial. And this is where I was going to go with this. There's notation for permutations, and we use a P. We use a P, okay? So now this is when the notation aspect of counting appears. So what we're really trying to figure out is how many ways can we permute? So permutations, there's a verb called to permute. How many ways can we arrange or permute 3 things out of 8 things? In this case, we're trying to find out how many ways can we permute the first 3 sprinters out of all of the 8 sprinters. So then we use this notation. So the first number as a subscript on the left side of P, this is the total number of objects we are considering. And then we're going to be choosing a specific subset of that number, right? Or a smaller number that's less than 8. In this case, it's 3. So what I'm saying is here is find the number of ways to permute 3 things out of the 8 things. So this is a number of permutations of 3 objects out of 8 objects, or from 8 objects. So obviously this number changes, right? As you change the number of objects that you have and the number of objects you want to choose to permute. So 8 factorial, so 8p3, you can say, right, is the number of ways to permute 3 things out of 8 objects. And how many ways is that? There's 336 ways every single time. It doesn't matter what you're speaking of. It doesn't matter if you're talking about sprinters. It doesn't matter if you're talking about cars, markers, I don't know, courses, schools. It doesn't matter what you choose for the object. If you have three of those things, if you have 8 objects and you want to choose 3 of them to permute, how many ways is that? That's 336 ways. So in general, this is the formula or the notation that we're using for permutation. So in general, uh, notation for permutation. So we use the letters N for the number of things. P, of course, is for permutations, and R is for the smaller number within, or it could, so R could be anything from N all the way down. Okay, so NPR is the number of permutations that can be made of R objects from a total of N objects. And then, of course, now we're going to start talking about we're going to be talking about formulas. So the formula for permutations is n factorial over n minus r factorial. And you can go back to the example we just did and see how that works. So if I wanted just to forget about the problem in the context of the problem and just consider it as a computational task, this is given the formula 8 factorial over 8 minus 5. Oh, pardon me, 8 minus 3 factorial, because that's how our formula is given. And 8 minus 3 is 5. So this is 8 factorial over 5 factorial. But what's 8 factorial? That's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And what's 5 factorial? 5 times 4 times 3 times 2 times 1. But because of multiplication being occurring in the numerator and in the denominator, and there's division in between that product, then the 5 factorial goes away. And so then we're left with 8 times 7 times 6. Okay. So what I want to say from at this point is that this definition or this formula for permutation, it's not that this came first. The argument for what permutations are is first, and then the formula is created or is formed or is developed. In a sense, if you just look at, if I were just to give you this formula, sure, you can probably compute this, no problem. If I give you like 5p2, right, you would be able to find what the number is if you just knew what the factorials were and you know how to plug in stuff and divide and cancel out, right? But if I were just to give you the formula without context to it, without an example, a concrete example of what permutations are, you wouldn't understand what you're actually computing. Like, you wouldn't get what that number represents. And so that's the difficulty sometimes of counting, because sometimes it's a very numerical computational task. So you, in a sense, you care only about just getting the number and getting the correct number as the answer. But combinatorics, this whole subject of counting, is really creating arguments. It's not an argument where you're talking back and forth with somebody. That's not what I'm talking about. I'm talking about an argument similar to when you create an argument in an essay, a thesis, right? In a way, of course. But you're trying to explain out the way to count something, and the argument, for example, here is that there's the first position, there's eight choices. The second position, there's seven choices. The third position, there's six choices, and therefore 8 times 7 times 6 is 336. That's the argument. That's the combinatorial argument. And because you see, I got the answer without using the formula, because I can extend this kind of argument to every possible way of permuting different objects, then it makes, and we know about factorials, then it makes sense that whenever we have n objects and we want to permute r of them, we already know, we're going to know that we're going to be considering the r places, and for each position we have n objects, and then we have n minus 1 objects, and we have n minus 2 objects, dot dot dot, all the way down. And so that's why we devised this, or someone devised this formula. It comes from the argument of counting, not necessarily that this came first. I hope that kind of makes sense. So creating these combinatorial arguments is actually more important than knowing the formula, because if you know the argument behind this, then the formulas kind of come, they kind of and they are easier to understand and to remember. Okay, so that is the formula for permutations. Oops, sorry about that. Let me just, yep, okay. All right. So here we talked about permutations. Great, great. All right, so let's compute a little bit. Let's compute some permutations, okay? So now I'm not going to give you like an actual example. I'm just going to give you some things to permute. So if I write, for example, 20p4, what am I computing? I'm computing the ways to permute 4 objects if I had 20 in total, right? And then using the formula, this is what? This is n, this is r. And using the formula, we have 20 factorial over 20 minus 4 factorial. So I'm simply using the formula. 20 factorial is what? 20 factorial over 20 minus 4 is 16 factorial. But then what do we know? We know that 20 factorial is 20 times 19 times 18 times 17 times 16 times 15, dot, 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 dot. But because I don't want to overdo it, I say this is 16 factorial. We understand what factorial is now, 16 times all the way down to 1. And I'll have the 16 factorial below. And so what happens is the 16 factorial cancels, and I'm left with what? 20 times 19 times 18 times 17. I could have gotten to the same position, to the same product, if I would have considered it as a combinatorial argument. If I would have said, hey, I have 4 spaces, I want to figure out how many ways can I permute 4 objects out of the 20. It's like saying, if I have 20 sprinters and I want to know who are the first 4 to make it through the race, how many ways are there for that to happen? Well, the first place, there's 20 possibilities. Once that first person is chosen, then we have 19, then 18, then 17. So I would have done the same thing. And then if you compute this, I don't know if some of you have already done so, you get 116,280. Okay. So I hope this is starting to make sense. I hope it does make sense. And again, this is just the beginning for counting. So we have to get comfortable with permutations. And once we get comfortable with permutations, the next step is combinations. And that's when things get really start to like to grow and get more interesting. So 20p4 is 116,280. Okay, how about this? How about 30p1? This should be quite straightforward. 30, right? If I have, how many ways can I permute one thing out of 30 things? I only have one to choose from in a way. So I have one object and I have 30 possible objects. So there's only 30 to choose from, right? So that's kind of straightforward. How about 30p30? Oh, hold on. Oh yeah, okay. Um let me just briefly just do the due diligence of using the formula. I just want to show something. So this is using the formula, right? So this is 30 factorial. This becomes 29 factorial. This is 30 times 29 factorial over 29 factorial. The 29 factorials cancel. I hope this is clear with the cancellation, right? You have 29 factorial, 29 times 28, 20 times all the way down to 1 in the numerator, and you also have the same thing in the denominator, so you can cancel them because everything's being multiplied to one another. So we get 30. Okay. So that was kind of straightforward, even if you didn't do the formula, if you just considered the combinatorial argument for 30p1. Now, how about 30p30? And then Sharon says 1. And I'm going to ask, how did you know that? Did you use the formula? Sharon, did you use the formula for this? You did it both ways. Okay. Okay. So if you use the formula, right, what are you going to get? You get 30 factorial over 30 minus 30 factorial. And then you get 30 factorial over what? 0 factorial. And then the question becomes, what in the world is 0 factorial? It almost makes no sense because you're saying 0 times 0 or something like that. That's what maybe you're thinking, right? It's just 0. So is 0 factorial 0? And some people say 0 factorial is 1. So for those of you who say 0 factorial is 1, why? Or how come? What's the reason? It's a rule. And who made the rules? Who said? Who makes up these rules? It's kind of so do you see how sometimes mathematics, some people, there's a whole philosophical debate. Is math discovered or is it invented? Is it that you just stumble upon it? Oh yeah, this is true. Oh yeah, that's right. This is 30 factorial. That's what it is. Or is it something that's kind of through human ingenuity able to be just sparked and created? So there's quite a number of people who believe that it's just discovered. It's just out there for us, because it is embedded in our world, physical laws and even subatomic um, laws of physics and chemistry and biology. Like it's just mathematics is there. But then there's some times such as this where it kind of just seems it's kind of arbitrary. It just seems that to make things work, because if 0 factorial doesn't equal 1, if it doesn't equal 1, then the formula for permutations is flawed. So that's why it goes back to what I just mentioned. The combinatorial argument is what makes the formula make sense. It's not the other way around. It's not that the formula makes the argument make sense. It's that the way we're counting things, we're we're reasoning out the way we're counting it. And so therefore it makes sense to create that formula. It's just that we have to make that little caveat, right? We have to say, hey, note something. So there is no context to this. That's the whole point. 0 factorial equals 1. There is no context other than saying, hey, if this weren't equal to 1, then the formula wouldn't work actually for every single possibility. Is it because there's one way to arrange it? You can say that, Christian. You can say, hey, how many ways there to arrange nothing? One way? But then it's like, how is that? So it's, I guess you can think of it. It does sound weird, right? Like, how many ways can you arrange nothing? I guess you can't say, yeah, there's one way. It's just don't do anything. If that's really what it is, right? But of course, it's a little weird to think about that. But yes, so this is 30 factorial over 1, which is 30 factorial. But let's say we didn't even know, let's say we didn't know the formula. It would still be 30 factorial, right? I have 30 things and I'm permuting it. I'm permuting all 30 of them. It's like saying this permutation is like saying, how many ways can I arrange 30 people in one line? Well, there's 30 spaces for this line and there's 30 people. There's 30 times 29 times 28 all the way to 1. 30 factorial ways. Alexandra, thinking of the tree is helpful for, is it saying why 0 factorial equals 1? For this example, yeah, okay, yes. Yeah, to arrive at 30 factorial, that's right. Right, the tree diagram is a good way, just as a basis, as a foundational way to interpret these numbers and these problems. But of course, we kind of graduate from that pretty quickly to just numerical computation because of the drawing the tree diagrams all day. You can lose your mind, really. But yes, the tree diagram is always a good thing to have in the back of your head when you do these things. Okay. Okay. Great. Makes more sense now, guys. So for the concert ticket question, it would be AP8. Correct, James. That is right. That is right. So you see how we build? We're building now our understanding of permutations, not just from a combinatorial argument perspective, which we reason things out as, as slots and these choices that we make. Now we're also using notation with these symbols, with this letter P. And so all of these things take some time to really mix and gel together. But once you have that really clear, then we can proceed. Okay, so very good. So far, so good. Okay. All right. So we understand this, I hope. Um, and then you can do all these problems with permutations. Okay. Now I think we can discuss for the last half hour, we can talk about um combinations. So I would say the bread and butter of counting deals with combinations. So what are combinations? How are they related or different from permutations? So right, hijab, it's unordered. So permutations, we care about the ordering of each object that we're considering. Combinations, we don't necessarily care about it. So it's an arrangement, though. It's still an arrangement. So combinations is an arrangement of objects where the order quote unquote does not matter. Now, what in the world does that mean? So all this time we're just talking about, yeah, things are ordered, we care about it, permutation, the factorial, and all of a sudden I just say, you know what, let's consider something that's it's an arrangement of things, but we don't care about the order. Then you're like, wait, what are we talking about? So like we care about order all the time, especially like for the lottery, right? When we how is the lottery won? It's won if you have the correct numbers with as well as the correct sequence of numbers. So if the winning numbers were like 24, 25, 37, and 39, for example, right? If you had four numbers to if you need to choose four numbers to win the lottery, we care about the sequence. That's a permutation that we care about. But we don't say, hey, as long as you get a 24 or 29, 37, 39, then you've won the lottery. We don't say that, right? So we're dealing with that kind of example where we have a selection of numbers or of objects, but the order doesn't matter. So let's try to see this with a very small number, a small example. So associated with counting and probability and so on and so forth, one thing that's important that I've mentioned is what we're dealing with is counting, right? We care about counting, how to count. Associated with counting, which is extremely important for to understand probability, there's something that's called set theory, and set theory is also extremely important to understand as a tool, as a concept for probability. So I'm just going to say what a set is, right? So a set is a collection of objects. Okay? That's all it is. It's like a group of things. That's called a set, but there's a lot you can talk about. There's a whole field on set theory, and a lot of other subjects in mathematics or areas of mathematics require understanding of set theory to understand that branch of mathematics. Particularly, we're talking about probability, so set theory is very important. So all I'm saying this is I'm mentioning this because I have a set of letters. Okay, so we're going to deal with a set of 5 letters. And we use notation for sets. We use these curly braces to create a set. So we're creating a set, and this set has the letters A, B, C, D, and E. Okay. Okay. And so now the question is, how many ways? So the question is very important. The way that I'm going to ask the question is important. The question is, how many ways can I select 3 letters out of the 5 letters, or from the 5 letters? Does everyone see the distinction with this question compared to the previous examples, the questions from the previous examples? Like in the other examples and previous to this one, we cared about how the ordering of things, right? How many people are in the line and so on. In this question, in this example, we don't care about how we select what's the first letter, what's the second letter, what's the third letter. We don't care about that. What we're asking is how many ways can I get 3 things out of 5 things? Which is it sounds like it's almost similar, but it's quite different. Yes, we'll have fewer results. That's for sure. Christian, can it be AAA? So that's one thing that's not going to be able, we're not going to be able to choose the same letter twice. It's like saying I have a hat of, I have a hat and you put, you have pieces of paper and each piece of paper has a letter in it, A, B, C, D, E, and you put these pieces of paper inside the hat and you have to select 3 of them. So if you select 3 of them, you're left with two are going to be left over. You can't choose the same letter more than once. So that can't happen. So hijab, yes, yes, very, very important. So see, these words are important. We are choosing, and it is an arrangement, but in this arrangement, the order doesn't matter. And henceforth, we're choosing. And this word choose is going to appear a lot, is going to be said a lot for combinations. We're going to be choosing things. So that's really a very good point. Right, right, Fernando. So ABE and EBA in this world of combinations are the exact same thing. So you kind of think of it like having different kinds of glasses, right? So if you wear the permutations glasses and you look at ABE and EBA, they're 2 different things. You take them off and you put on the combinations glasses and you view things differently. And then you say, oh, ABE is the same as EBA because you're viewing it from a different perspective. You're just saying those letters are chosen in both groups. ABE and EBA are groups of things with the same things in them. So they're the same. That's because you're only viewing them as groups. If you look at it as a permutation, you're caring not just about the group of letters, but you care about the order of them. So they're different. Does that make sense? So then, even if it doesn't, we're still gonna go through this, okay? So then let's break this down with things that we've just spoken about, which are permutations. So then you're like, wait, I don't know exactly yet how many ways I can select 3 things out of 5 things as of yet. I don't know. So why don't we break it down this way? Why don't we break it down by saying, how many ways, how many total permutations? So then you're like, wait, what? We're talking about combinations. So why are we talking about permutations? Well, that's why it's kind of like we have to learn permutations first to know combinations because it's built upon, really, combinations are built upon permutations. So how many total permutations can be made of 3 letters from the 5 letters? And this should be easy now, I hope, right? Because we just talked about permutations. So how do we compute that? Jayton, I like the example. I like that example you said. Right. It's 5p3, right? Which is what? 5 factorial over 5 minus 3 factorial, which is what? 5 factorial over 2 factorial, which is what? 5 times 4 times 3 times 2 factorial over 2 factorial. Sorry, a little messy. The 2 factorials cancel, or you could just multiply 5 times 4 times 3 if you looked at it that way, which is fine. And so then how many ways is that? There's 60 permutations. What does that mean again, though? What does that mean? I know what 5 times 4 times 3 is. I know I could do that in a calculator. I can do that by hand. But what does that mean when we talk about the context of our problem? What does that mean? There's 60 permutations of 3 letters that can be made out of 5 letters. What does that mean? Anybody? You see? You see how that there's 6 versions of ordering 3 letters? No, there's 60. Yeah, yeah, there's 60. And what are those 60? Are we gonna write them out? You gotta be kidding me, right? It's like that kind of thing. So like if I were just to give you an idea, I would be writing this A, B, C. That's one permutation. Then what would be another one? B, A, C. That's another one. And then I would do all of it, and there's 60 of them. We would have D, E, F, and then we would have E, F, C, and then there's 60 of these guys, like all over. That's a lot, right? I'm not gonna do this to myself. But we don't care about the ordering. So then we're like, wait, what? I don't get that. Why are we counting the number of permutations if we don't care about the number of we don't care about the permutations themselves? So that's step two. Step two. Step two is how many. So selecting one of these guys, select one of them, select one permutation. I have 3 letters, right? How many ways can I permute 3 letters? How many ways can I permute 3 letters? It's 3 P3. It's 3 factorial. It's 3 times 2 times 1, which is what? 6 ways. I hope you guys see the connection. I hope you do. So you're like, okay, there's 60 permutations overall. And then there's for each permutation, for one permutation, ABC, there's 6 ways to arrange those letters. There's ABC. There's what? ACB. There's what? BAC, which is already here. I should maybe use something else like BCE. Are you going to divide 60 permutations by 3 factorial? Wow, Alexandra. Wow. Let me just say that. I'm gonna answer your question, but I'm just gonna say wow. Do the opposite instead of start from the highest number down, go down to the smallest. Oh, I don't know exactly what you mean by that. By the highest number down, you go to the smallest. We are doing factorials, um, but instead of 8 times 7 times 6, you do 3 times 2 times 1. Yeah, that's what we did. That's what we did with part 2. So part 1 was how many permutations are there? How many total permutations can be made if you select 3 letters out of 5. So you have 5 choices for the first letter, 4 choices for the second letter, and 3 choices for the third letter. There's a total of there's 60 permutations. I have, if I were to write all of them out, I have 60 possibilities of permuting 3 letters out of the 5 letters that I have in the beginning, right? And then I'm saying, okay, select one of those permutations. How many ways can you permute them? There's 6 ways. So for each of these guys, for each version, there's 6 possibilities of permuting them, right? So I was just gonna write them down. So ABC, ACB, BAC, BCB, BCA, and then let me write this down. And then we have CAB, right? And then we have CBA, right? So what are these? What are these? These are 6 permutations. Fernando, excellent connection. Yes. Wow, you guys are good. Very good. You guys are seeing that's exactly what you should be doing every single time. You should be trying to be making connections as we go. As you go, the quicker you're able to make those connections on your own, the better it will be. So then what do we just figure out? What did we just figure out? Do you see how we're counting as a way of organizing? Like it's a way of organizing. Combinatorics is a way of organizing how to count. We're just organizing our way of counting. So we're not just willy-nilly saying there's 60 permutations. We're saying that there's a group of 6 permutations, right? And for each group, there's 6 permutations. So then if there's 60 total permutations, and for each group, there's 6 ways of arranging them, then the question really is, how many groups are there? And that's, yeah, we just want the groups, exactly. And that is why Alexandra made a great point. You're dividing essentially. So the question is, how many groups of 3 things can be made out of 5 things? How many groups are there? How many groups of 3 letters out of 5 letters are made? And then we say, well, there's 60 permutations. And we divide it by six permutations of those groups. And this gives us 10. There's 10 groups. It may take some time to think about this and make and for it to make sense. Essentially, why am I dividing the 6? That's really the question. Like, why am I dividing the 6? How is that related to the 60? It goes back to what is a combination. A combination is just a group. It's a selection. It's a choosing of things. We don't care about the order of them. So in our world of combinations, ABC, ACB, BAC, BCA, CAB, CBA are the same combinations. Of course, permutations are different, but in combination world, they're the exact same thing. And not only is this one group of things that are the same, we have another one. We have another one. We have another one. They're the same. And I think it shouldn't be F here. Sorry about that. It shouldn't be an F because there's no F that we're talking about. This is like AEC or ACE. So essentially, what are we finding? We're finding the groups of letters that we can create out of those, the groups of size 3 out of 5. So that's what this 10 is. 10 is there's 10 groups of 3 letters that can be made. If they were to be chosen out of 5. If they are to be chosen out of a total of 5 letters. And now you can think of this, you can extend this, forget about letters. Like when we form groups of people, committees, presidents, a lot of people do this, secretary, vice president, and yeah, like group members in a project. If you have 5 people and you only want to choose 3 of the best to present, so you have a group of 5 people and you're working on a project and you have to present, and you say, hey, we need 3 people to present. There's 5 of us. How many ways can we create a subgroup of 3 people out of the 5 that we are here? And there's only 10 different ways. And in that context of that question, we don't care who's the first chosen, second chosen, third chosen. We just care how many ways can I select 3 people. So that's why the combinations is more of a selection or a choosing of groups than an ordering of people or of ordering of objects. Does that make sense? Do you see how combinations are a bit more complex Like it's just a nuance to them that it makes you really think about what you knew about permutations and what you know about counting now. Because you're like, wait, what is this that we're doing? It's more than just dividing 60 by 6. That's what I hope you guys see. It's more than just multiplying 3 times 2 times 1. It's more than that. You see that? Of course, 3 times 2 times 1 is 6. Of course, 60 by divided by 6 is 10. Like, of course, we know this. But the real question is why the 60 divided by 6? Why are we choosing these numbers to divide? What does this number that we get mean? Like that is the important part, and that's the hard part. But once you're able to do that, then counting becomes actually a fun thing. And then so someone mentioned this, very important. So, and the reason why I brought this up is because this is 5p3, right? This is 3p3, which is really just 3 factorial. So let's generalize this. How do we generalize? So in general, what does that mean for combinations? In general, this is combination notation. So not very creative here. Of course, we use P for permutations, and guess what we're going to use? C for combinations. And we're going to say what? N, C, R. And when you see this, what are you computing? You're computing the number of groups of size R that can be made out of N objects. Now, I hope that makes sense. Combinations, when you have NCR, means out of the N objects that you have, I want to know how many ways can I create how many groups are there possible that I can create if each group had R things in it. So in our example, we had 5 letters. How many ways can I select 3 letters out of those 5? And there's only 10 ways. And what's the formula for this? Someone mentioned it already. This is the formula. It's n factorial again. N minus R also appears. So there's this permutation aspect of it, which we talked about in part 1, right? 5p3. There's this permutation aspect to it. But then what did we do? On top of that, we divided it for each permutation. We divided it the number of ways to permute that permutation. So in a sense, what we're doing is we're getting rid of the copies of it, right? We are dividing out the copies of those permutations that are repetitive. So we're saying that for each permutation or for each subgroup of letters, there's 6 permutations for each. But we're not treating each of them as individually. We're treating them as one unit. So that's why we divide. And this is my formula. This is it. So embedded in this formula is are permutations. You're taking a total number of permutations and you're dividing out the permutations for each group. So when you do that, you're left with the number of groups. Do you see that? So you're rearranging the total possibility, the space of total possibilities. You're rearranging them in a very organized fashion. So you can think of the 60 objects, the 60 permutations. You can think of them as columns of. There's 10 columns, and for each column there's 6 possibilities. So you're organizing your counting space. You're organizing this. I just want to say this class is improving my handwriting as well as my understanding of counting. I am so glad that you feel that way about your handwriting being improved, because I feel like my handwriting is not getting improved. It's just I get kind of like excited and just start writing quicker and like I'm like, oh snap, I shouldn't be. Look at this S. This is terrible. Look at this N. Oh my goodness. I'm see now you're gonna make me really think about writing my T's and crossing my T's and dotting my I's. You see that? There we go. Notation. Hey, I appreciate that. I never thought about creating my own font. That would be cool. I don't even know how do you create your own font? That would be, oh my, I don't know. That'll be interesting. But does that make sense? Yeah, yeah. This gets really fun. Um, we have 3 minutes. Okay, so now we have an understanding of combinations and we know how to interpret them. Uh, there's a few more things I want to say. Um, so one thing about this is that the notation eventually we're gonna graduate. Yeah, that's right, Christian. That's right. That a combination is just a permutation, but now we're using permutations to get rid of permutations in a way, because we don't care about the ordering of it. We only care about the selection of those objects. But we're gonna have to graduate eventually or move on from this notation of NCR. For now, it's okay, but especially when we talk, well, yeah. But I'm gonna show you the proper way or the more formal way of talking about combinations is known as what's called the binomial coefficient. And it sounds complicated. It sounds like you're talking about some crazy stuff. I'm just gonna give you the notation for it. It's not a fraction. I know some people already think about fractions when they see this, but this is not a fraction. This is called the binomial coefficient. And this is simply NCR. It's just a notation. This is the same thing, okay? It's just that the binomial coefficient, why they call it that way, is because the numbers that are come from, like, this is when things get interesting because someone, I think Alexandra, you brought this up when in your introductions about counting or something, and you heard probability and you thought about Pascal's triangle. And then this is when you're like, wait, is mathematics really discovered then? Because the numbers on the Pascal's triangle, and I'm like, first of all, how did Pascal even come across this is already impressive in itself. But the numbers in the Pascal's triangle are binomial coefficients. So let's just briefly like compute this, right? So if I do, for example, 3C1, right? You can even, you don't even need a formula for this. You can even reason this out. If I have three things and I want to choose one of them, how many ways can I do that? How many choices, how many groups of one thing can be made out of three things? Three. Thank you. Yes, that's right. Three. There's three ways. And then, but look at this. How many ways? How many ways? How many groups of two things are there that can be made out of three things? We'll save the suspense. It's also three. How many ways can I select nothing out of three things? How many ways can I select a group? Yeah, exactly. It's one way. And then how many ways, how many groups of size three can be made if I do out of three things? Well, I have three things. I can only choose three things. So there's only one way to do that. So these are all binomial coefficients. And if you remember Pascal's triangle, for those of you who remember, it's a recursive, so it's like a recursive um, set of numbers. We start with 1, right? That's the first row. Then the next row, we extend these ones, right? The next row, we still extend these ones to the right, but then the numbers inside now are the sum of the previous two numbers. So 1 plus 1 is what? 2. And then the next row, we extend these ones again. So these ones diagonally just keep on, like they just keep on going. But the numbers in between come from the previous two numbers that we have. So 1 and 2, when you add them, what do we get? 3. And 2 plus 1 is what? 3. These numbers 1, 3, 1, 1, 3, 3, 1 are coefficients, are given, our combination, our numbers that come from combinations. 1 to 1 is what is, for example, what's the second row? This would be what? 2C0. What's 2? 2C1. And what's 1? 2C2. Each row of Pascal's triangle is the binomial coefficients out of the objects that we, yes, I know. Sorry, guys. I went a little over time, but we'll talk about this next time. I hope you guys have a better understanding of this. Sorry for stopping so abruptly.